draw a latching circuit. So when we draw a latching circuit, we have our 230 volts on the left hand side and our neutral on the right hand side. So live on the left, neutral on the right, or 24 volts on the left, 0 volts on the right. So notice here we have input 1, which is our normally open switch, and on the right hand side we have our output. Input 2 is a normally closed switch, that's the stop switch, and input 1 is the start button. Notice that input 2 is normally closed stop button. When push to make input 1 is pressed, the output will be on. The contactor will close, latching on the output switch. The circuit is now latched on. Input 2 is a closed position already. When pressed, the contacts open, breaking the live to the output. The latch is broken due to the contactor being de-energized. Understanding the inputs. So here we have on the left hand side where we are using a negative common, and notice there, if you look here, this is our negative common, and out of the power supply we can see it says 0 volts. We have all these connected here to the lights, so this is our negative common. But coming out of the system is what is alive. So when this contactor, when this inputs switch on, they will switch on these outputs at the bottom of the PLC, and they will throw a live to the lights. On the right hand side we will notice that it's the other way around. In this one, it's the live that is being fed all the way to the lights, and the contactor is actually switching on a negative to the lights. So it can be used in either operation. We call the left hand side the PNP output, and we call the right hand side the NPN output, where we are switching a live on the left hand side. On the right hand side PLC2 we are switching a negative. So in other words, when the light receives a negative, it is switching on the right hand side. Notice the wiring, either a live common or a negative common. Understanding the inputs. So on the left hand side we have switches coming to position number 1 on the in, switches position number 2, and here we have output 1, output 2. So we can see that output 1 controls a lamp, and the PLC is programmed that switch 1 and switch 2 are both connected to output 1, and switch 3 and switch 4 are both connected to lamp number 2. We can see this by looking at the ladder logic diagram on the right hand side. In the ladder diagram, switch 1 and switch 2 control lamp 1. The switches can be programmed as an on and off. 3 or 4 or both switches can control lamp 2. 1 and 2 logic and 3 and 4 switch logic OR. Understanding the inputs. So what does PLC stand for? PLC stands for Programmable Logic Controller. So we call the switches discrete inputs. In the center we have the PLC unit. It's the central processing unit, CPU, and on the right hand side we have the contactor. So the contactor switches on the motor, and that's our output. So PLC, Programmable Logic Controller. So the CPU is where all the calculations are performed. The PCU runs the PLC program. Understanding the diagram. When the forward push button is pushed, M1 contactor is energized and will close auxiliary contact M1. The forward direction the forward direction is now latched on. When the reverse push button is pushed, M2 contactor is energized and will close auxiliary contact M2. The reverse direction is now latched on. Normally closed M2 and M1 will prevent the other contacts being energized at the same time. Understanding the times. So here, this is the output of this is a VFD, a variable frequency drive that produces something called pulse width modulation. So it makes use of insulated gate bipolar transistor switches on the output side. So either these switches work in combination to produce short on times, longer on times, or shorter on times. In effect, it is trying to produce a wave. So switches conduct first in one direction and after a certain time in the other opposite direction. The motor sees these pulses as an AC wave with rising and negative pulses. Controlling the time of each pulse by shortening the time results in the control of the frequency of the waveform. All this takes place at the DC to AC converter of a VSD. VSD controls the speed of an AC motor by varying the frequency supplied to the motor. So this diagram is normally called a block diagram. We have the converter, which converts from AC, so three-phase AC to DC. Then we have the filter, which consists of a capacitor to smooth out the ripple. And then we have the inverter, which converts from DC back to AC. The entire process is controlled by a microprocessor, which monitors incoming voltage supplied, the speed set, the output voltage supplied, and the current to ensure operation of the motor is within the operating parameters. Understanding the inputs and the outputs. So here on the input side, we have the AC to DC converter. We have the filter, which smooths out the ripple in the center. And here we have the IGBT, DC to AC inverter. So inverters convert from DC power, DC voltage to AC voltage. The first part converts the AC supply to DC voltage by a rectifying circuit. Each pair of diodes rectifies one of the three phases of the three-phase system. The second part smooths the AC ripple out using filter capacitors. This gives a pure DC voltage on the DC rail. The third part inverts the DC to AC voltage at a different frequency. The IGBT are switched on and off in order to create pulses that are called pulse width modulation. Understanding the inputs. So on the input side, we have the diode bridge rectifier, the filter, which consists of the capacitor. We have the inverter that converts from DC back to AC. And we have the voltage and frequency control that controls the speed. Speed control by voltage to frequency control measures the current vectors in the relation to the applied voltage. Here we have regenerative braking. So we have a three-phase AC supply coming in. We have a variable frequency drive, a braking unit. We have a resistor to take up the excess energy. And we have a weight that comes down. Therefore, the motor will accelerate, moving in a downward direction. So regenerative braking is a form of braking in a motor-driven loads in which the loss of kinetic energy from braking is stored and then fed back later to provide power to the motor. Regenerative braking occurs when the motor on the load rotates faster than the motor. For example, when a lift is descending, the motor holds back by applying a negative torque. The motor acts like a generator, creating extra electrical energy This system rids this regenerative energy via capacitors if the motor is VSD controlled. When motor is VSD controlled, DC capacitors charge and store this regenerative energy. When the charge across the capacitor plates becomes excessive, it is then fed to a braking resistor, where the resistor becomes hot and dissipates the heat energy. What is the standard operating voltage of a PLC? 5 volts. What is the main advantages of hard wiring? Easy to trace a circuit along its wires, easy to fault find by following the physical wires. All sensors and contactors are physically connected via wires. Name the components used to get rid of regenerative energy. A braking resistor. Name 3 sensors used as input devices. Light sensor, proximity sensor, and a temperature sensor. Name 4 advantages of a soft wire system. Lower cost, requires less space, more flexibility, simplicity. Name 4 advantages of a soft wire system. Less maintenance, relatively cheap when compared to the use of relays. PLCs are more flexible than the previous relay control systems, easier to troubleshoot. System upgrading is easier. Save space. State the functions of an opto-isolator in PLC. It's a semiconductor device that uses light to transfer electrical signal between circuits while keeping them electrically isolated from each other. State the function of an opto-isolator in a PLC. An opto-isolator, also known as an optical coupler, photocoupler, optocoupler, is a semiconductor device that transfers an electrical signal between isolated circuits using light. It is used for communications in PLC control to prevent high voltages from affecting a lower power system while assisting the signal to pass. Name the 3 steps that a PLC has to undergo to complete one program scan cycle. Input scan, process scan, and the output scan. Name 3 examples of analog input devices: switches, pressure pads, and sensors. Name 3 main types of proximity sensors: ultrasonic proximity sensors, inductive proximity sensors, capacitive proximity sensors. VSD stands for variable speed drives. VFD stands for variable frequency drives. VSD is used with the following types of motors: AC, asynchronous squirrel cage, induction motors. VSD is used with the following motors: AC, asynchronous squirrel cage induction motors; AC, asynchronous motors with a permanent magnet stator. VSD is not used on DC motors.